Alright guys, we're going to wrap up 11.1 today. We talked about on Monday chi-squared tests and kind of like went over the basics, talked about goodness of fit. I want to review a lot of that and kind of just practice a little bit. Don't forget your homework was on the previous notes. It was page 693, I believe. And that's going to be due Monday. And you will have a 11.1 quiz early next week. I don't remember the exact date off the top of my head. All right, check my website for details. Okay, big thing to remember is that chi-squared was about categorical data. Everything we've done most of this year has been quantitative, and we are finally back to categorical. All right. This is just a quick little example to kind of review everything we did on Monday. And I chose an example that was something we've kind of been familiar with a long time, a six-sided die, just to make it a little bit easier. So we've got Jenny rolling a six-sided die that she made. She's going to roll it 60 times. Each side was to test to see if each side is equally likely to show up. So the idea is we have to see if her die is fair. So when we're doing our hypotheses, the null should be that we assume the die is fair. Now, if we put that into more statistical verbiage, we're talking about the distribution of all the different possible values, 1, 2, 3, 4, 5, 6. We think the true distribution of die rolls is evenly distributed, which is just another kind of more specific way of saying the die is fair. And then, so our alternative, remember chi-squared, there's not really a way to prove that a distribution is greater than or less than, so it's always like a not equal to type thing. So we were just saying that the same thing is true, but we think it's not evenly distributed. Okay. So that was the basic idea there. That's going to be the same for the majority of what you're doing. You think a distribution is true, and then you think it's not true. Okay, so here's the next part. We're going to do our expected counts. I want to point this out. Assuming that her die is fair, think about the hypotheses. That's another kind of fancy way of saying assuming the null is true. Okay, I want to point that out because we're going to eventually get a p-value and make some sort of conclusion based off of it. And the whole idea with p-value, every time I've asked you to interpret, it's always based on the null being true. The idea of innocent until proven guilty. So just want to point that out in the wording there. All right, calculating the expected counts. So remember, expected counts is if this is truly true, how many of each roll should I be getting? So if they're equally distributed, that means that each roll should have the same chance of being chosen. So if this part's true, should be a 1 out of 6 chance for each outcome. And so if you think back to the M&M example, if we had a sample size of like 14 M&Ms and 14% of them were supposed to be brown, then you found 14% of 14. On this, they did 60 rolls, so for each outcome, the expected count would be 1/6 of that. So each outcome, that means rolling a 1, rolling a 2, and so on. Each outcome's expected count is going to be 1/6 of 60, which hopefully y'all can do that math. That's 10 rolls. Now, if you look at down here, here are the results from the actual 60 rolls. So you'll notice it didn't work out perfectly. We were expecting 10 for each roll, and there's some of them where we had more than 10, there's some that we had less than 10. So that was observed minus expected. So remember, chi-squared is kind of measuring the weirdness of your data. How weird is it to get these results when we were expecting these? Okay, so calculating chi-squared, the formula was that you took the observed value and subtracted the expected. So I'm going to do 13 minus 10. You're going to square that value, and then you're going to divide by the expected. Now, when you're doing this, I don't really expect you to have to do this for every single 6 and like show me all that work. Mostly with free response stuff, if you will just show the first few terms plugged in. So I just plugged in the outcomes for 1 and 2, and then kind of do ... We got the message, you know the formula. And remember, this formula is on the formula chart. And then for the rest of this, I'm just going to kind of use some calculator work and maybe do this in my head. The fact that I'm subtracting 10 makes this a little easier to do in my head. The difference here is 3. Square that, you get 9. Divide by 10. The first outcome discrepancy is 0.9. The next one, 11 minus 10 is 1. Square that's still 1. Divided by 10, it's 10%. And so on. So if I do the next one, there's a difference of 4. Square that, that's 16. So this is going to be 0.16. Or actually, apologize. That'll be 1.6. And then the rest of it would be plus 0.4. Now, do you notice here how 10 and 10, that one actually had the exact amount of rolls we were expecting, so that piece would be 0, and the next one would be also 0.4. Okay. And then if you add all that up, you get 3.4. Alright, so that is our chi-squared. Remember, that's just measuring how far away your actual data was from what you expected on this kind of big picture over the entire distribution, because each little piece is kind of a different, has a different difference, and this is an overall big picture. Look at how weird the data is. Okay, and now you've got your little chi-squared distribution. We talked about on Monday how it's a rightly skewed distribution, no longer normal, because the lowest you can possibly get is 0, and as you get a bigger and bigger, weirder chi-squared, it becomes less likely. So we, depending on where our scale is, we're somewhere way over here. It doesn't seem like it's going to be that big of a deal. Okay, and so now we find our p-value. That's finding the area under our curve. We had two options, just to kind of review this real quick. The chi-squared table, I gave you all this yellow page. Remember, you find the degrees of freedom first. So you use your degrees of freedom, which is no longer based on the sample size. It's based on the number of categories, which we have 6 outcomes. So 6 minus 1 would be 5. You use that to look towards the center of your table. So I'm going to go to 5. And then we look around here for what is closest, or where does our chi-squared fall. Now my chi-squared was 3.4, which is less than the first value here at 6.63. So I use my degrees of freedom to say that, okay, it's less than that first value. And then you use that to work up to the top part of this. The probability of our tail here is going to be, it's not 0.25, but if you'll notice, these are getting bigger and bigger as you move to the left. So if it's supposed to be a little further to the left of this column, that means it's going to be more than 0.25. So all I figured out is that my p-value is supposed to be less than 0.25. So the table you can use, but it doesn't give you a precise value. You could still use that to make a conclusion. Anything more than 2.5 is bigger than any kind of significance level, so we would fail to reject. So that's not a big deal. Or your other option was to use the calculator. So this was the table, and this is the calculator. It's the chi-squared CDF, which we've used. It's in that same menu as normal CDF, this distribution menu. Your lower bound is the 3.4, the upper bound is infinity, and you get your degrees of freedom of 5. And if you plug that in, you'll get a more specific value. In this case, it should be 0.64, okay, which is definitely more than 25%, and that's definitely a big chunk of the data up here, so my graph makes sense up there. Okay, so we've kind of got through the pieces. Now you'll notice I'm working your way through the 4-step process for the most part. We did our state. We haven't really touched on the plan as much. We'll get to that. This is our do step, finding our test statistic and finding our p-value, and then we've got our conclusion. So based on this p-value, 0.64 is definitely greater than any significance level we would typically use. In this case, I'll use the typical 5%. Oh, excuse me. So we fail to reject the null, which again, be very careful with how you word this. That does not mean, if we go back up here, does not mean that we can say that the die is fair. We can just say that we don't have evidence that it's not fair. It's kind of that double negative idea. So we would say something like, there's not convincing evidence the die is unfair. And I could use the wording from my hypotheses a little bit better, but yeah, hopefully get the idea. Again, just be very careful that you don't accidentally in your wording accept our null. Okay, so I mentioned a second ago how we hadn't really talked about the plan. We talked a very, very brief minute on Monday, but I want to make sure we get to that. This is the plan step where we talk about the conditions needed to do a chi-squared goodness of fit test. So good news, the first two are kind of the same that we've done in lots of different testing procedures or inference. You need to either have a random sample or a randomized experiment. And be careful because the wording does change depending on if you're doing a sample or an experiment, and some of us learned that the hard way on our last test. Second one was our independence, which does not happen very often, so more likely than not you check the 10% condition to see if your sample size is small enough. And then here, just like everything else we've done, is the weird condition that's not the same. And this is still checking, not normality, but it's checking to see if your distribution is considered a chi-square distribution up here, like this little rightly skewed thing. So we have all the expected counts, not the observed, the expected counts have to be greater than or equal to 5. Some things to remember with that. Those values that we calculated back up on part B in this example, those are always based on the percentages or the proportions in the null, the stated distribution, not based on your sample. Because we're not using the observed values, we're looking at the expected values. The other thing is the word counts. We're using actual not integers, but we're using actual numbers, frequency, not the proportions themselves. So go back and look at part B. Go back and look at our M&M example if you want to see more of that. Okay, so that was just kind of the basics to get us back into it. On the back here, we're going to do a more probably rigorous problem. I might recommend pausing the video here and just seeing how far you can get through the problem, reading through it first and all that. And then you can always come back whenever you've gotten to the point where you're not sure what to do next. Okay. This one is interesting because we are looking at a lot of information. There's a 2000 census where we looked at all, I'm going to point this word out, all U.S. residents, right? Census means they talk to everyone. And they broke it down by age groups. So they've got the 20s, the 30s, the 40s, and the 50s and 60s and so on. So that's the just who falls into that age group. Now, they took a sample of U.S. residents to get this data right here. So this right here is going to be our sample data. These are the observed numbers. Now, more specifically, these came, the members of the sample were chosen by randomly selecting or randomly dialing landline telephone numbers. And we want to find evidence that the age distribution of people who answer this, so the sample that are based on the landlines, is not the same as the age distribution of the U.S. residents. And there's probably some speculations you could make. We typically say landlines are kind of going out of style, so the younger generations don't have them. So we're going to see if this data kind of holds up those ideas. It might help kind of organize your thoughts if you think about this is the observed. So all these percentages they gave us up in the top, that's going to be our expected. I'm going to organize those thoughts real quick. It's the ages versus the percents. So the 20s was 19.1%, the 30s was 21.5%, 40s was 21.1%, 50s was 15.5%, and I'm running out of space. The 60s and plus, the 60 and over crowd was the last number, 22.8%. Okay, and these are going to give us the expected percents. So we're looking to see if this matches up with this. Keep in mind, these are still in terms of percents, and these are not. All right, so let's do our four-step process. Our state. The null hypothesis is going to be that we think the age distribution of all U.S. residents matches the landline survey. So we would say something like age distribution of landline survey takers is the same as the age distribution of all U.S. residents. Keep in mind, if you're having trouble with wording, borrow from the problem stem. Okay, and then again, I don't really recommend taking the time to write all of that again. I'll just say, we think it's not the same as all that. Okay, so that's our basic idea. Might want to mention the fact that we're going to use our typical 5% significance value. Let's get into our plan. All of the basic ideas still the same as what we've always done. We are going to mention which test we're doing. We're doing a chi-squared goodness of fit test. That abbreviation is completely fine. You can use that. If the conditions are met, it did mention up here that it was randomly dialing telephone numbers, so random sample. It ended up being 1,000, random sample of 1,048 landline users. Now, we can't randomly select somebody multiple times, so it's not independent sampling, but we can say that 1,048 is less than 10% of all landline users. And technically it's landline users 20 and above, because like I would assume if they had a child answer the phone, they didn't talk to them, because that's not where the table shows us anything. All right, and then the last one was the expected counts being greater than 5. We have not actually found those yet. Be careful. These are not the counts. These are percents. So I have to figure out what is 19.1% of my sample size. So that first one would be 20.2. Okay, and then I'm going to save a little bit of time. If you do that with every single percent, show your work, but just for time's sake, here are the next numbers. If you just work through this table. Which hopefully you can see all are definitely greater than 5. 1, 2, 3, 4, 5, so 20s, 30s, 40s, 50s, 60s. Okay. All right, so that's your plan. Now for the do step, again, I am not going to take the time to write all of that out, but it's the observed. So for the 20s, we had a sample of 141 people minus the expected 202. Square that over 202. I'm going to show one more. So for the 30s, we expected, we observed 186. We were expecting 225.3. Square it, divide by expected, ... I will save you guys a lot of calculator pushing and tell you that the chi-squared is 48.2. Now, if you think about what the previous problem was, it was 3.4. That is a very big difference. All right, if you think about your graph, we are much further out on that rightly skewed tail. So don't be surprised when you get a very small p-value. Okay, I would go do your chi-squared CDF. It's just faster and nicer. Lower bound, upper bound. Now, degrees of freedom, be careful. Remember, it's based on the category. So there's 1, 2, 3, 4, 5 different age groups. So -1, degrees of freedom is 4. Okay, go plug that in. But I'm going to tell you right now, it is so small. It's in that scientific notation we've seen before, so it's practically 0. Okay, which is what I was saying. This is a very weird chi-squared. It's very large, which means our data is super weird. So it makes sense that it's pretty significant. Okay, so when we conclude, 0 or approximately 0 is definitely less than 0.05. So we get to reject the null, which means we do have evidence. Go back to what I was asking about. We have now provided evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution for the U.S. residents. So you can kind of use that to answer or to word that. I'm going to let you guys handle that. Like I said, it's right there. All right, now, good news. This do step is doable in the calculator. I think in first period I did kind of hint at this on Monday. But if you go to your stat test menu, it should be, I believe, D. Now there's going to be a chi-squared test that we'll talk about. We are very specifically doing the goodness of fit test. And I do want to point out that if you're using, or if you happen to pick up an older calculator, the TI-83s, which are like the more old school, just black and kind of, I think they have some yellow detailing, does not do chi-squared goodness of fit, but all the ones that I've issued, I don't think anyone's using an 83. Everybody should be okay, but just let me know if that's an issue. To get credit for your do step, just make sure you provide the very bare minimum, which is getting the chi-squared. You do want to give the degrees of freedom because think about your table. Degrees of freedom does definitely change how the chi-squared is used. And then the p-value. Okay. So up on the previous problem, I would have just said chi-squared at 48.2, degrees of freedom equals 4, p-value approximately 0. All right, so that is goodness of fit. We have done this officially now. The last little bit is what we call a follow-up analysis. That's not any kind of fancy thing. It literally just means look at your data and let's make some possible connections between what we've seen. Now, for when should we do this? If you're thinking like practical in real world, think like your end of the year project possibly. Whenever you get to reject the null, whenever you have significant results, it's always a good idea to go back and see if you can kind of connect some of the pieces for why something ended up being significant. When we're talking AP exam, don't do this unless they ask for it. Now, what is it? Like I said, you're kind of just going to go back and look at the data and say, like, does any of this make sense? Why am I getting a really, really weird data sample? Why am I getting really significant results? So to kind of help you do this, look at the individual categories. In this case, it's the different age groups. Look at your categories. Look specifically with ones that have large deviations. If you think back to the die example we did on the front, there was a few, like that roll of 5 where there was literally no deviation. We got 10, we expected 10. Whereas there was like a 6 and a 10 that has a deviation of 4. So you're looking for larger deviations from the expected. And you want to look at the direction of the deviation. So if you think about it, if you're always doing observed minus expected. If you get direction means if you get a positive, that means observed is greater than expected. If you get a negative, that means that observed was less than expected. And that can sometimes be telling as well. Okay, so let's just try this so you can kind of see how it goes. I did this in the calculator when I was calculating at 48.2, but just to kind of show you what's happening here, I'm just going to calculate these deviations, just this, and not like the full chi-squared piece. So for the 20s, the deviation is the 141 minus 200.2, and that's a difference of negative 59.2. So this is the age group, and this is the observed minus expected counts. 30s, the deviation was negative 39.3. 40s, it was 2.9. 50s, it was 48.6. And the 60 plus crowd was 47.1. So just looking at that, I can definitely see a trend of the more extreme age groups have larger deviations, the middle age group being by far the smallest deviation. And more specifically, look at the direction. The younger two age groups are negative deviation, and it gets kind of smaller. And then it starts to get bigger in the positive direction again, with these two being practically the same. But think about what that meant up in the previous thing. If I was just to kind of make some wild guesses at the beginning of this whole thing, I probably would have said that younger kids don't pick up landlines. They don't have them, or they don't pick them up, or whatever the case may be. And this does seem to kind of support that idea. We got less than we expected in the younger age groups, and we got more than we expected in the older age groups. So just put that into words. I would basically say something like, the younger age groups had fewer people answer landline survey than expected. You could even mention that it's expected based on the distribution of ages in the U.S. While the older age groups had more than expected. And then I maybe would connect the dots and say this supports the idea that younger generations won't have landlines, or maybe if you're doing a survey, will be underrepresented in landline surveys. That might be a good, nice way of using our statistical vocabulary of underrepresentation. Will be underrepresented in landline surveys. Okay, so that's kind of the idea. Again, don't overthink that. It's just kind of looking at the data at a more micro level and just kind of observing anything. I'm not saying for sure that there's a connection between age groups and landlines, because this is just one sample. But based on the sample, it does kind of hold up to what we would think is true based on just, you know, kind of social knowledge. All right, that's it. Chi-squared. Okay, again, homework due Monday. That's it. All right, bye guys.